Here's the first step where we have hexamethylene diamine reacting with adipic acid to make nylon 6,6. So a diamine implies that there is one amine group and another amine group on the same molecule. So there are two amine groups on the same molecule, and that they are bridged from one another by a hexamethylene. Methylene indicates the carbon unit in the middle. So notice at this point that we have a parentheses 6. This does not indicate a polymer, but rather that there is a simple small extension of CH2s to separate the two amine groups, okay? So while this has the ideas of a polymer, the number 6 is not long enough for us to consider hexamethylene diamine a polymer. Similar thing is found in the partner reagent adipic acid. So we have 4 CH2s in a chain, and then finishing off that chain that is only 4 carbons long is a carboxylic acid on either end. Okay, so here we have 2 carboxylic acids. Okay, and so we see here that a carboxylic acid is reactive towards an amine to make an amide. Okay, and in doing so, you can see here highlighted through the red that we have the opportunity to eliminate water, and this is therefore an appropriately termed condensation polymerization reaction. So for every carboxylic acid that reacts with an amine, we eliminate one water molecule, and our first amide for the polymerization is shown here. And we notice that the other components of the rest of the molecules have not reacted but remain reactive. So here's a carboxylic acid that was unused that is still reactive. Carboxylic acid. And here's an amine that is still reactive over here. So this new molecule that we've drawn by just making our first amide molecule is still reactive towards other condensation steps to propagate the chain and grow further. So we can show that here a little bit further, show that once more, where we might expect this carboxylic acid product to also react in a similar way. So perhaps another hexamethylene diamine comes in and we can make a reaction product here now and make a linkage, okay? So we would also show the elimination of water in that case. And so the product there to show another propagation step would be H2N6 and H, showing our first amide that we had originally, CH2, we have 4 of those, and now we have our new amide, and now our new remaining fragments from the hexamethylene diamine. So here we have an amide and an amide on the same chain. Okay, so to show the repeating pattern here ultimately, let's maybe do some color coding. Notice that the hexamethylene diamine can be recognized there by having nitrogens flanking either of the 6 positions. So that is kind of shown here. Okay. And then the other adipic acid, we can cartoon that as green. That is shown here. And so we're seeing most of that structure right here. And we might expect the next one to be located here if the situation continues, and perhaps even another one here. So you can see there's an alternation of the adipic acid with the hexamethylene diamine down the length of the chain. Okay. We saw on the previous slide, so for every amide group that was made, that we eliminated one water molecule. So we better show that here for completion. So we'll show plus H2O to indicate the new one that we've made given that new amide group that's formed. And to ultimately show the repeat unit here, if you wanted, we can try to do that. We're going to need to just open up this end. Okay, and so I want to be able to capture in my parentheses the blue and the green pattern. So I've pulled out the hydrogen to indicate that that hydrogen is not going to, we're not going to see a NH2 repeating in every repeat unit, but only an NH. And if I were to stop here, I complete my blue piece, and if I keep going, I eventually get my green piece. And then to terminate that pattern right here, I would then allow for the pattern to continue. So here we have both units captured, and ultimately that would be the repeat unit there. Okay. Good. And if that were N, we know that within the parentheses I have two amide groups, recognizing one here and another one here, as we see, that would occur at every repeat unit down the length. So we would expect 2N water molecules for every repeat unit that was made. Okay, so hopefully that gives you some clarity here on the information on this slide. Here we're seeing a lot of those polycondensation polymers shown. So we've now seen how we make this polymer with its repeat unit shown on the table. This is, of course, nylon 6,6, famous molecule for making fabrics. Related molecule is the polyethylene terthilate, which has an ester functional group in the main chain. We recognize that. To show the sort of pieces needed there, we're going to break away and show this as terphthalic acid that's needed for the synthesis, and then the ethane diol that is right here. Okay, so we're going to show those, and we'll show you how this polyester is made on the previous slide. I'll just make some space there. Okay, so let's go there. Clean this up. Terphthalic acid, we need 2 carboxylic acid groups. Okay, again, 2 on the same molecule. And then we'll put, so this is a different polymerization here. This is making polyester. And we'll put our ethane diol, so CH2, OH. And we're going to try to make a polycondensation product here, eliminating water. So we're going to eliminate that. Okay, so I'm already expecting plus H2O. Okay. Okay, and then I'll just switch. So we know we're going to make a new bond here. We're going to go to our carboxylic acid. We've eliminated the H2O here. And there we go. So this is our new bond made. This is our ester. So this is how we make the polyester that is central in the bonding in the main chain of polyethylene terthilate. Made one ester group, so I eliminate one water molecule. To show how this might happen over and over again, well, we know that we're going to have to eventually put the blue piece kind of over here. Okay, So if you're getting comfortable with this, you can kind of cut to the chase and show that with parentheses ultimately. Okay, so I have to capture one of the blue pieces and then one of the red pieces and make sure that the pattern for connectivity continues. Okay, so I'm going to cut that off right here because I know the CH2 has to be connected to an oxygen, and I'm going to consider the next unit over here. So my eye is tracking from here all the way to here to make sure the connectivity pattern is correct. So oxygen, CH2, CH2, oxygen, C double bond O, etc. So that's the repeat unit for the polyester. Within that, I have one ester group that's clearly identified here, another ester group over here. So each repeat unit has two esters, so I better have made 2N water molecules if I make this. Okay, so that is N units of this plus N units of this would give us the polyester that is polyethylene terthilate. Okay, and so for the last topic, we'll just talk about side chains quickly. So the example where we start substituting off hydrogens from polyethylene to install side chains shows that we have some more complexity options here. When those side chains are all positioned on the same side of the main chain, we term the polymer isotactic, same iso. And so this could be the chlorides, this could be the benzene rings for polystyrene. We can have isotactic polymers if we can control how monomers are added and how the side chains are positioned relative to their neighbors. In syndiotactic, the pattern is alternating. So without question, the side chains alternate from one repeat unit to the next to position these side chains on opposite sides of the chain as we walk down the length of the main chain. If there's no pattern to how the side chains are positioned and are rather positioned randomly on one side versus the other, we term the polymers atactic. An important consequence of this is that with irregularity in the main chain, we suppress crystallization, so this material would only be amorphous. It would not be able to crystallize, whereas the regular pattern of side chains would allow polymer chains to align and organize and interdigitate side chains or position side chains in a regular pattern between neighboring molecules and ultimately allow crystallization. So these two polymers would be termed semi-crystalline given that they can crystallize. Okay, and so that's it for today. I think we'll end there. If you are still needing some more background in some of the organic chemistry or the fundamentals anyway, I invite you to review the fundamentals that I posted for this course, as well as reach out to me for further assistance. Okay, thank you.